I love power series, partly because we couldn't live the way we live in the world without them, and partly because the results are just so elegant. To understand this, you'll need to know about exponential notation, or raising things to a power, series and series notation, factorials. We cover that in our video on permutations, combinations, and N-choose-R. And in fact, we have videos in this series about all of these things. Trigonometry and graphing the sine wave, differential calculus using the addition rule and the power rule, and that's it. Now, when we think about creativity in different fields, including mathematics, people often talk about the collision of different ideas. Power series came about through the collision of three different ideas. One was a big problem, one was a piece of vaguely and only vaguely interesting mathematics, and one was a piece of complete mathematical whimsy. Once these ideas collided, what they produced was not only the capacity to do statistics of things like finding the area under the normal distribution curve, which is fundamental to a fair bit of what happens in statistics, but is also needed for things like, well, most modern electronics, in fact, structural safety calculations, so entering into a high-rise building or driving over a bridge knowing it's going to be safe. Automatic control systems for communication networks, power grids, transportation, so therefore the internet, among other things. Navigation, so therefore trade, having a wide range of goods, as well as statistics, so life would be really different without them. Now, the big problem, if you think about an equation like y equals 8 times x cubed plus x squared over 5 factorial, you may not want to calculate it out, but it's not that hard to calculate out with a pencil and paper, and certainly not hard to calculate out using a calculator once you're given a value for x. So if x equals 7, we can work that out without too much difficulty. That's not the problem. The problem is if there are some other things like, for example, y equals sine x, where if you knew that x equals 7, that wouldn't necessarily help. Unless you have a calculator to work it out, but well, they didn't in those days, but then for now there's a question of how would the calculator work that out? Back then they would prepare tables, but the question was, how do you actually go about preparing the tables without using a protractor and a ruler, which is obviously prone to errors. And for an example, just using trigonometry for navigation that was relevant at the time, if you wanted to sail from England to the Caribbean and you made an error of 1 degree in your calculation, you'd miss the mark by 119 kilometres or 74 miles by the time you got there. So in terms of precise navigation, this was a big problem. In terms of the vaguely interesting piece of mathematics, when we looked at finding the differential calculation, calculus rather, the first time we looked at the equation y equals x squared and found that the derivative of that is 2x. We're going to change the notation here. Rather than talk about graphing x against y, we're going to graph x against function of x, which is essentially the same thing, except that this notation is just a bit easier for what we're going to look at, which is taking the derivative of the derivative and the derivative of that. You'll see there where we've got f apostrophe in brackets x equals 2x. That apostrophe, we call that f prime of x, and that means this is the derivative. So the function is x squared, the derivative of the function is 2x. And if we graph that, x against the derivative of x, we get a straight line, 2x. If we take the derivative of that using the power rule, we find the derivative of the derivative is just 2. Looks like that. If we take the derivative of that using the power rule, the derivative is 0. And so we can take it. So the vaguely interesting piece of mathematics is that we can take derivatives of derivatives. We can find not just a slope of the tangent to a curve or the rate of change of the curve, but we can find the rate of change of the rate of change, the rate of change of the rate of change of the rate of change, and so on. But this is where Brooke-Taylor reasoned trying to solve this problem if we had some function that we couldn't easily calculate, except perhaps at one point, say where the value of that function equals 0. We could calculate, or where the value of x equals 0. We could calculate the value at that point, and we could calculate the derivative of the function, the derivative of that, the derivative of that, and so on. Then we'd know the value of the function, particularly at, say, x equals 0. It was actually, just a side note, Taylor worked out a way to do this for any value of x. That makes it look more complicated and harder to learn, so we're just going to work for our purposes where x equals 0, and this is technically called a Maclaurin series, because Maclaurin was the one who said, well, I can simplify what Taylor's doing to make it easier to understand. So we're going to follow that, but essentially the ideas came from Brooke-Taylor, which is all we need to know about that history at the moment. But what he said was, if we could calculate those derivatives and we knew the value of those things at a point, say 0, then we'd know the value of the curve, we'd know the rate of change of the curve, we'd know the rate of change of that, we'd know the rate of change of that. So at that value, at that point, we could have a pretty good approximation of what the curve should look like. And if we could come up with a polynomial, which we can find the value of, and it happened to have the same values of the derivative at where x equals 0, or so the same value of the function, the same value of the first derivative, the same value of the second derivative, and so on, then that polynomial, if we graph that, would give us a very, very close approximation of the function that we couldn't calculate, at least fairly close to the area we're looking at. So at least around the region of 0 or wherever else we looked at it, we should be able to approximate that closely and therefore work out how to calculate the value. So if we think about sine now, if we graph sine here, we're graphing the angle along the horizontal axis and the value of the sine of that angle on the vertical axis. We get a curve that looks like that. If we do the same thing with cosine, we get a curve that looks like that. And what we find, and we're not going to prove this here, we'll prove this in the book, How to Love Statistics, when you haven't done the maths, but for now just recognize that it's true that the value of the slope of the curve of the sine wave is going to be the same as the value of cosine at every point. And likewise, the value of the cosine is going to be minus the sine. That new graph, or that new line we put in there, is negative sine. It's the sine rotated on that horizontal axis. In other words, if our function is sine x, the first derivative is going to be the cosine of x. The derivative of that is going to be minus sine x. The derivative of that is going to be minus cosine of x. We're back to sine x, and we keep repeating that. And as I say, that I'm not proving that here. We do have a proof in the book. But based on our definitions of sine and cosine, it's quite easy to calculate those values, 0, 1, 0, minus 1, and 0. So that's the first part of our problem solved. But now the problem is, if we have some function like this, say sine, where we can work out those values and can work out those derivatives and the subsequent derivatives, how do we find a polynomial that will match that curve? And this is where the mathematical whimsy comes in. Taylor realized that if you take a polynomial with subsequent powers of x, starting with x to the 0, which is just another way of writing 1, and x to the first, which is another way of writing x, and the letters there just represent the coefficients, just the numbers, any numbers that you multiply those powers of x by. If you take that polynomial, keep it going indefinitely, and divide each term by the factorial of the index of x, then something really interesting happens. We call that our polynomial of x. And if we take the derivative using the power rule, then we multiply each of those terms by the index, reduce the index by 1, and that's what we're left with. And now if we change the way we write those factorials, so we're writing 2 factorial as 2 times 1 factorial, the same thing, 3 factorial is 3 times 2 factorial, 4 factorial is 4 times 3 factorial, etc. It's exactly the same thing. And now we can do some cancelling out. The first term disappears because it's multiplied by 0. In each case, the number that we've multiplied our term by cancels out with the first number of the factorial. And what we're left with is almost the same as our original polynomial, except that each of the coefficients has moved up. It's almost like 9 in the bed and the little one said roll over. They all rolled over and one fell out. So each coefficient shuffles up the line and the first one disappears, and that's the only difference when you take the derivative. And when you keep taking the derivative of that, then all you keep doing is shuffling those shuffling those coefficients further up the line. And then what he realized was that if you look at each of those polynomials at the point where x equals 0, then all of the terms except the first one disappear because they're all multiplied by 0. So the value of the polynomial at 0, the value of its derivative is going to be the value of the first coefficient. The value of the derivative of the polynomial at 0 is where x equals 0 is going to be the value of the second coefficient. The value of the derivative where x equals 0 is just going to be the value of the third coefficient, and so on. So suddenly he had a way of coming up with a polynomial, any polynomial, where he could straight away write in the values of the polynomial at those subsequent derivative levels, and do that really easily. So there's the value of our first derivative, there's the value of the function at x equals 0, the value of the derivative of x equals 0, the value of the derivative of x equals 0, etc. Let's look at some examples of this to see how neatly this works out. Let's take our function x squared. We know the derivative of that is 2x, the derivative of that is 2, the derivative of that is 0, and so on. And if we look at the value of that where x equals 0, we get 0, 0, 2, and 0. So 0 squared is 0, 2 times 0 is 0, 2 is just 0, and 0 is just 0. And if we put that into our Taylor polynomial and say, well, x squared should be approximately equal to that based on what we've talked about so far. First term's going to disappear, second term's going to disappear. In fact, all the terms multiplied by 0 are going to disappear. The 2 that multiplies 2x is going to be is going to cancel out with 2 factorial, and what we're going to get is x squared is approximately x equal to x squared, which obviously it is. In fact, it's exactly equal to x squared. We'll take a more complicated one, the expression we looked at the beginning of this video, 8 times x cubed plus x squared plus 5 factorial. That's the first derivative using the power rule, second derivative, third derivative, fourth derivative, and then they're the values when x equals 0, 0, 0, 2 on 5 factorial, 48, and 0. Put those into as the coefficients in our polynomial, and the zeros disappear. And what we're left with is just x equals 8x cubed plus x squared on 5 factorial is equal to 5 squared on 5 factorial plus 8x cubed, which it obviously is. So this actually really works. Now if we look at sine, we said earlier that the first derivative of sine is cosine, derivative of that is minus sine, the derivative of that is minus cosine. We get back to sine, keep cycling round. Easy enough to put those values in. If we put those values into our polynomial, all the terms that are multiplied by 0 disappear. 1 times x to the first over 1 factorial, that's just x. Minus 1 times x cubed over 3 factorial, that's just minus 3 cubed over 3 factorial, and so on. What we're left with is sine x ought to be approximately equal to x minus x cubed on 3 factorial plus x to the 5th on 5 factorial minus x to the 7th on 7 factorial plus etc. etc. So the sign alternates, and we have using only the odd numbers, but apart from that what we've got is actually a Taylor series without coefficients, or the coefficients are just the no, that's right, it's a Taylor series without coefficients, just using the odd numbers and alternating signs. Let's look at how that works. There's our graph of sine x, and there's the value where sine x is equal to x. That's what the curve looks like. That's what it looks like when sine x equals x minus x cubed on 3 factorial. So we're just calculating this out to 2 terms, and you can see that already close to 0, that's a very close approximation of the curve. But the more terms we calculate, the closer our approximation ends up getting to sine x. And in fact, because the sine x keeps, or the derivatives keep repeating themselves, you get into a repeating pattern of what subsequent derivatives look like. You can take that polynomial out, and if you take it out to infinity, you don't just have an approximation of sine x, you've got an exact way of writing sine x, which is really quite remarkable when you think that sine x started out, we calculated it by the, in a right angle triangle, it's the opposite of the hypotenuse, and yet we can calculate it using that very neat polynomial, and we can calculate it exactly if we go to enough characters to do it. It's one of the beautiful things of Taylor series. Using series notation, we can write that like this, and that looks worse than it is because that first minus 1 to the n, where n starts at 0, that's just a way of writing, saying that the sign is going to alternate. So minus 1 to the 0 is 1, minus 1 to the first is minus 1, minus 1 squared is 1, minus 1 cubed is minus 1, and so on. The second part, that 2n plus 1, that's just a way of writing odd numbers. So when n equals 0, 2n plus 1 is 1. When n equals 1, 2n plus 1 equals 3. 2n times 2 plus 1 equals 5, etc., etc. So it's just a way of saying we've got alternating signs and odd numbers in our series. Now if we look at cosine, and just get rid of that sign, and now we're looking at the cosine of x as our function, so the derivative is going to be minus sine x, the derivative of that's going to be minus cosine of that x, the derivative of that's going to be sine x, etc. And they're the values when x equals 0, 1, 0, minus 1, 0, and 1. If we put those into our Taylor polynomial, then each of the terms multiplied by 0 is going to disappear. 1 times x to the 0 over 0 factorial is actually just going to be 1. And that's what our polynomial is going to look like. So there's our polynomials that represent cosine of x and sine x. They're almost the same. They've got alternating signs. They're very close to the Taylor series, except that sine x starts with x and uses odd numbers. Cosine of x starts with 1 and uses even numbers. And there's our formula, which would be very easy to write into a computer and is easy to program into a computer. That calculation for sine x to whatever degree of specificity you want. Cosine, it's even easier. We've got the first, that minus 1 to the n represents alternating the signs, and 2n, that's just a way of saying that we're looking at even numbers. That's Taylor series. Thank you for watching.